What we're going to talk about today, and ideally get all the way through the next 35 slides, which I will fully admit is not going to happen, but we're going to attempt to, is very, very repetitive. So we're looking at each of these individual types of classes of our carboxylic acid derivatives and addressing each of their chemistries. Okay? The most important aspect to realize is that we can start at the top, we can go to our acyl chlorides, and all the chemistry that we talk about can go all the way down. If we start with the amide, going up is virtually impossible. Okay? We have to do very special chemistry to change the reactivity of our amide around enough that we can then start to propagate further to the top of our food chain. Okay? So the chemistries that we'll address, while they can apply fairly equally well to each of these, because in all cases what we're looking at is reacting these with very strong nucleophiles. You can't interconvert between these upwards. You can only interconvert downwards. Okay? So in each case, your acid derivative, you're looking at an electrophilic carbon, which means all of the next sections of material, we're now going to go through and look at each of the possible nucleophiles. Why are each of our carbonyl carbons electrophilic? Why are those carbons all electrophilic?
You have partial positive charge and the oxygen withdrawing electron density.
We've got the oxygen withdrawing electron density giving us partial positive. Take it a step further. We also have an atom Z, if we will, which the textbook has nicely labeled in red so it stands out a little bit more. Okay? Notice in the case, or in each of these cases, that atom Z is one of your most electronegative elements. Okay? In all those cases. Chlorine's a little bit weird, but it's also really high electronegativity. Okay? So all of those are going to withdraw electron density from that carbon, making that carbon extremely electrophilic, which means put it with a nucleophile and we're good to run. Okay? So let's looking at reactivity, we've kind of addressed those. We have also talked about this chemistry already, believe it or not. Okay? What does our ketone look like? What would atom Z be in the case of a ketone? Some carbon. What is atom Z in the case of an aldehyde? Hydrogen. Why does the chemistry for the acid group change so drastically from the ketone and aldehyde?
You don't have the electronegativity differences.
So we have a difference in electronegativity, which makes that carbon less electrophilic in the case of our ketone and aldehyde, but there's another more important issue. The chemistry that we're seeing with our acid groups is also ultimately an addition and elimination. When we look at our ketones and aldehydes, we very rarely got the elimination with our electrophilic carbon. Why did we not get the elimination in those cases?
Those aren't good leaving groups.
There's no good leaving group. So the big difference when we're looking at our acid chapter is that our atom Z's in all of these cases are relatively good leaving groups in comparison to hydrogen and carbon. Okay? So that's going to be one of our other big driving factors behind this. We're going to end up effectively keeping the carbonyl in most cases, okay? Because we have that leaving group ability. So our nucleophile can come in and attack, break the pi bond first. Why do we break the pi bond? Higher energy, reform the pi bond, and kick out our leaving group. Okay? It's a bit silly of me to do it there because I have a feeling the next slide is exactly what I want to do. Yeah, freaking awesome. Okay, so we'll start with our carbonyl with atom Z. Okay, I don't particularly care what that is at this point. And I'm going to have a nucleophile. Good symbol for a nucleophile would be N. We could add a little bit more detail. What other characteristic would we expect on our N? Lone pair electrons. Maybe even a negative charge. Those electrons will come in and attack. our carbon. What happens? How many bonds does that carbon now have? Too many bonds, so what do we have to do? We'll break the pi bond. The result? You know, that looks like an oxygen in the middle. We'll have our atom N and Z, and our oxygen will be negatively charged. Okay? At this point, what we have is the tetrahedral intermediate. Why do we call this our tetrahedral intermediate? Because it's tetrahedral. Okay? So one of the issues with our tetrahedral intermediate at this point is that we have some very electronegative elements attached to it. We've got our oxygen, our Z group, and ultimately our nucleophile can also effectively be very electronegative. So carbon, not wanting to completely give up all of its electrons, eventually calls back for some electrons from one of those groups. Okay? The easiest one, or at least the one that we'll see in most cases, is from our oxygen, comes back down. Now how many bonds does that carbon have? 5. So we have to break a bond. What bond do we break? Okay. In nearly all cases, we're breaking Z. If we broke our N bond, what happens? Go back in the reverse direction. Okay. Depending on what our Z and N are, we might very well see these reactions happen in equilibrium. In the case of our acyl chloride, what do you think? Would we expect much of an equilibrium? Why not? Chloride's a really good leaving group, which means it doesn't act as well as a nucleophile, or at least comparatively to whatever nucleophile we're adding. So we don't see a lot of that reverse reaction. So what you're ultimately doing is comparing your Z to your N and deciding, are they going to compete with each other? If they can compete, then yes, we've got equilibrium. We've got to be a little bit more concerned about what's going to happen in the reaction. If they aren't going to compete, it should be fairly unidirectional, and we just push across. Okay? Based on past experiences from the ACS test and most of your exams for that matter, okay, do we ever really ask a question where no reaction occurs? Very, very rare to see that type of question. So if you see two things mixed with each other, a good first guess, something happens, do that exchange, particularly when it comes to carbonyls. Okay? If that gets you an answer, go with it. If you see none of the products formed, that's usually kind of a semi-panic inducing mode, at least for me, and I would probably skip it and come back to it later. Okay? So when we're going through and looking at each of these mechanisms, we're looking at least 2 steps. This can change, okay, depending on if we're under acidic conditions or basic conditions. Based on what's drawn up here now, what do you think, acidic or basic? Why basic? Okay. Look at the negative charge on that oxygen. Okay. If it's under acidic conditions, we would not expect to see that negative charge. Okay. We could also, depending on what atom Z was, Z has a negative charge as well. Also, very likely we're not under acidic conditions. Okay. If it's basic, then everything looks good. If it was under acidic conditions, we would have to do a reaction or pre-acid-base reaction before we could go through and do our addition elimination here. That pre-reaction would be to activate the carbonyl oxygen. Have it react with a hydrogen. What would charge would that oxygen build now? Positive. Does oxygen want to be positive? Nope. So what does it do? Takes the pi electrons. So it pre-activates the carbonyl carbon, making it super electrophilic so that it can react better with a weaker nucleophile. Why does it necessarily have to be a weaker nucleophile under acidic conditions?
You can't have a negative charge.
Can't have a negative charge in solution. So your nucleophile, if we're under acidic conditions, must be weaker. Okay? It can't have that negative charge in the presence of acid.
So would your Z group leave then?
What's that?
Would your Z group even leave then? Would you just get like that second one with an H off the O?
You'd get the H off the O. We still have 3 electronegative groups attached. Oxygen still panics. Okay, so we will still always form that tetrahedral intermediate, and that tetrahedral intermediate will always decompose. Which way does it go? To the starting material or towards the product? That kind of depends on the individual circumstances. Okay? Eventually, once you got to the end, you would end up pulling off that hydrogen that was on the oxygen. Okay? We already talked about the weak pi bond, so I think we're okay with that. Preparation of your acid chlorides. Okay, we said those were the absolute highest reactivity carbonyl or acid derivative that we could work with. Okay? Turns out there's really only one reagent that you guys need to be concerned about to make your acid chlorides. Okay? So let's take a look at this. To get an acid chloride, we need chlorine. Where did that come from? So if we think retrosynthetically, what do you think? You think the carbon and the oxygen were probably still in there? In our R group?
One of those chapters where we had the AlCl3.
Okay, so there's an interesting idea, trying to get the AlCl3 to help us out. But what did that aluminum trichloride do?
Well, that would take the chlorine off.
That takes chlorines off. We want to put a chlorine on.
So we're using the
Okay.
SOCl.
So the reagent that we're going to end up using is the thionyl chloride. What did thionyl chloride react with? Anybody remember that? Alcohols. Effectively, OHs. We're starting from a carboxylic acid. So if we would look at a general mechanism for this. Whoa. Oh, goody. Internet just died. Maybe it's still working. Okay. Variety of different ways of showing this. Let's see. Okay, it is still working. Our thionyl chloride looks like this guy. Okay. Anybody see anything particularly reactive about thionyl chloride? Double bond, which is going to do what?
Oh, I'm sorry.
If it acts as a nucleophile, it's sharing electrons. Where would the electrons be shared from? Not there, okay. We could even kind of get into that, but I would say there's an easier argument here. Take a look at that double bond being the most reactive. Where do those electrons spend most of their time? On the oxygen. Why? It's more electronegative than the sulfur. So the oxygen does become slightly nucleophilic, but when we looked at carbonyl chemistry, which is effectively the same interaction, did we really address the oxygen as acting as a nucleophile? No. Why not? It kind of goes with resonance. Oxygen doesn't really want to share its electrons. Why not? It's electronegative. It doesn't want to give up its electrons. We can give it up to something quick and small and easy like an acid, okay? But having it act as a nucleophile and reacting with something much larger, not very likely, okay? Because it can't get its electrons back as easily. Okay, so our oxygen could be nucleophilic, but we just nixed that. What happens to the sulfur?
Partial positive.
Becomes partially positive, which means that sulfur could act as an electrophile. Okay? How electrophilic is that sulfur? What else is attached to that sulfur? Chlorines, which are very electronegative. The sulfur in thionyl chloride is a wicked good electrophile. So what ends up happening is that we can take lone pair electrons from one of our oxygens, and it depends on which mechanism you're going to look at in this case, okay, and react with our sulfur. I believe this is the version your textbook uses. Make sure I get all my atoms in here. That's a really bad negative. Sorry, I must have been looking at it twisted. Okay. Does that oxygen want to be negative? Nope. So what happens? You can kick the electrons back down. Okay, but then sulfur has too many bonds, so what can we do?
Break one to chloride.
Break one of the bonds to our chlorine and kick that out. Okay. Why is that important? What did we just generate now? Right out here? A really good leaving group. So our chloride can now come in, whoops, attack, kick out our leaving group, and we end up with which looks pretty darn close to what we wanted to get, right? Okay, what's the issue?
You gotta get rid of that carbon, or hydrogen rather.
We got to lose that H+. How can we get rid of that H+? Yeah, some kind of base floating around in the solution. There's a couple ways that we can do that. We can do it just with anything that's remotely basic within this. Okay, but what are the odds we have very basic things in here?
Low, 'cause
Very
carboxylic
low.
acid.
It's carboxylic acid. So typically, one of the things that you'll see attached along with this is not just SOCl2. So now I'm going to turn my retrosynthesis arrow around. You'll see SOCl2 to swap our OH for a Cl, but you'll also see PYR, which stands for pyridine. What can you tell me about pyridine? It's a pretty decent base. Okay, it's not a strong one, but it's a pretty good base. Not only is it basic, but it is not nucleophilic because it's super large. That was my interpretive dance.
Good.
Okay, so that can help us eliminate or remove that hydrogen and help facilitate the reaction along.
But really, you can just use any base at that point. Add it on.
Any base, you would just typically want to avoid a nucleophilic base. Okay, so in that case, pyridine's a big one. TEA, triethylamine. Can I erase stuff to be able to draw that? I'm good to erase? Okay, it's all disappearing. Triethylamine is a good one. Very sterically hindered, same general idea. We have that lone pair to act as a base, but it can't act as a really good nucleophile. Why is that other stuff there? It's not on my screen. That's weird. I can't even erase it. Okay, so that can be one of the other things that you might see there. TEA, trimethylamine even, you could get rid of hydrogens. LDA isn't too nucleophilic, but it's a bit of a strong base to be able to go through and do that. A little bit more than you need. Wow, I can erase it. I just can't see that I'm erasing it on my screen. There it is. Hey, look at that. Okay. So your thionyl chloride, you not only have to remember from your alcohol chapter, but you're going to have to remember for the acid chapter to get it to that acyl chloride. Once you're in that acyl chloride state, now you can do all sorts of crazy reactions. Okay? So all of those crazy reactions are what we'd be looking at next. Okay? If we start with an oxygen nucleophile, okay, well, we just said that our carbon on the acyl chloride was electrophilic. Okay, so the lone pair electrons on our alcohol can come in and attack. We break the pi bond first, reform the pi bond, kick out the chloride, and we end up with our product. What functional group do we have? We have an ester. So what we've gone through and done by reacting with an alcohol is shifted one state or two stages lower in that reactivity sequence. Okay? What if we'd used water? What would we have ended up with as a functional group?
Aldehyde.
What do we end up with? Our oxygen comes, well, I should probably erase some of those arrows. Our oxygen comes in and attacks, breaks pi bond, breaks that, kicks that out. And what do we have? We've got our R group, carbonyl. Jeez, can't seem to hold on to things. Officially, we'd have that, not particularly stable, so what happens? Deprotonate, and what functional group do we have now? The carboxylic acid. Okay? So that gets us a couple of those stages. What else could we react it with that's still an oxygen? What was one of the other intermediates we could have ended up with? take the acetate ion, so we deprotonate an acetic acid molecule. And what happens? We now have our nucleophile, comes in and attacks. What do we get as a result? What atom is attached to my carbon? And oxygen. What atoms are attached to that oxygen? Carbonyl, carbon, and carbon. What functional group do we have here? Not a malonic ester. And it's an anhydride. Okay, that was one step down in our reactivity. Okay, so ultimately all we're doing is changing the nucleophile to get to whatever we want. Okay, so it's identifying that piece and just kind of shifting it along. Why do we have the pyridine in there? Okay, in the case of the alcohol. We'll talk about this in a little bit too. We need something to remove the hydrogen from our alcohol. So one of the things that we can do to help speed the reaction is add a little bit of pyridine. That pyridine will deprotonate our alcohol after it's attacked, and we can end up with our final ester a little bit quicker.
So if you had any of the lower in that reactivity series, and you wanted to get to the very top, you could do the reaction with water to get that carboxylic acid, and then do the SOCl2
Yes.
pyridine, get up to the top?
So to get to the top, we have to have the carboxylic acid. So do whatever you got to do to get to the carboxylic acid, and then react it with a thionyl chloride. You're now up to the top, and you can work your way down any way you want. Okay? All you have to do at that point is supply the nucleophile, and you're now good to move. Okay? Does that make sense? So your question or statement was absolutely valid. Okay? In the case of the alcohol, we added the pyridine. What if we wanted to make the anhydride? Do we need the pyridine?
No, it's already deprotonated, no?
We don't need the pyridine in the case of reacting with the carboxylate salt because that's an eraser. It's already been deprotonated. Okay, we've already used the base to remove that hydrogen. We don't have to worry about it. Okay? So the anhydride's going to be kind of nice. We don't have to worry about that secondary addition of base. Okay? Questions on that?
I don't really follow what you're saying. So if we just add like water to our OCl thing.
So what he's asking is starting at any lower stage, how can we get up to the top? To get to anything lower, okay, or to go from anything lower to the top, we have to get the chloride on there. The only way you can get the chloride on there is using thionyl chloride. What did you have to react thionyl chloride with to get to that top? It had to be a carboxylic acid. So if you start with anything within that sequence and you're trying to get it to the acyl chloride, you have to turn it into the carboxylic acid first, add the thionyl chloride to put you back up to the top. Does that make sense? Okay. We could look at nitrogens as nucleophiles. Okay. Since we changed the nucleophile, I didn't draw it on that same slide. Okay. It's still the exact same concept. Our nitrogen now acts as a nucleophile, attacks at our electrophilic center. Okay. Break the pi bond reforms, we kick out the chloride. We end up with an amide. Okay? One of the things that's kind of obnoxious with our amines, if you remember that from, I think it was chapter 20, okay, where we're looking at some amine reactivity, is our primary versus secondary versus tertiary amines can sometimes act differently. Thankfully, in this case, they all react the exact same. Okay? Which one would you expect to react fastest? Would we expect the top one to get to the product faster than the bottom, or vice versa?
The top.
Why should the top one react the fastest? Steric hindrance. Okay. NH3 is a much smaller nucleophile. It's going to be able to get access to that carbonyl much more quickly than, say, our last one, okay, or our secondary in this case. Okay. Would we expect the tertiary to work? Tertiary now has 3 R groups. Okay? It could go through and attack, but then what would our product be? Okay, the last one will be the easiest one for me to show it on. If instead of having that hydrogen, I make that an R group,
Don't you get a positive nitrogen?
I get the positive nitrogen. Is that a very stable thing to form? Would we expect the tertiary amine to react as a nucleophile? No, which is good because, remember in the previous steps, we used it as a base. Okay? If it acted as a nucleophile as well, we'd have problems. Yeah.
I know we've already talked about it, but why do you need the two equivalents of amine?
Yeah, we hadn't quite gotten there. So let's address the issue with the amine. Okay, and we'll address this more when we move into the amine chapter. What is a characteristic of our amines? Let's go all the way up to the very top one. Okay, and I did draw it on there, the lone pairs, so that it could act as a nucleophile, right? What else has electrons? What's that? Fair enough. What other type of species? So we got nucleophiles, bases. Why is that a problem? Okay. When we go through and run this reaction, we said a base is helpful to have around to remove a hydrogen. When we look at our starting material, we have NH3. When we look at the product, what do we have? NH2. Where did that hydrogen go? To anything remotely basic in solution. What's basic in solution? The NH3. So if I start with 2 acyl chlorides in 2 of the amines, remember we can only run one reaction at a time. One amine attacks, one of our acyl chlorides is down, but now I have that acidic hydrogen. I need something basic to pick it up. What's basic? The other equivalent of NH3. So what happens? If I put in 2 equivalents, one acts as a base, one acts as a nucleophile. So if I only put in 1 equivalent, I get half of my possible product because one of the other ones had to do some different chemistry.
The other byproduct of that be?
So if we had to look at our byproduct for all of the, well, not all of these, but for that first one, we would have NH4+. Okay, and for each of the preceding ones, this one I guess would be NH, R, NH3+. Okay. Freaking irritating as all hell when it comes to nitrogens. Okay, you have to remember that basic characteristic. So when you go through and do nitrogen reactions, be aware of that. We ran into similar issues like this when we talk about Grignard reagents. Okay, if you think about all the way back, probably even into the lab, I gave you that reaction and said the Grignard reacts with this ester and we get the triphenyl methanol product instead of benzophenone. And it was, well, why? Well, the intermediate benzophenone was more reactive than your starting material. Same kind of idea is happening here. We get one to react, but we now have this reactive species that has to be canceled out by our reagent. So we end up killing the reaction partway through. Okay? So if I get sapling homework up and running, which I should, and we'll try and make them short assignments as far as the acid and the amine chapter go, be very, very careful when you see nitrogens. On almost all cases, they are expecting you to show the nitrogen as protonated and your acids, if they're present, deprotonated, because the nitrogen will remove that hydrogen. Okay, so you have to be aware of that secondary chemistry. Okay, and that's why we have those 2 equivalents. Okay. And this is where you see those 2 equivalents show up a little bit more. Okay, if we look carefully at the mechanism, there's our second equivalent, making the NH4+. So if we started with 2 of each of these, okay, at the very end of this, we'd have one of our products, 1 NH4, and now 1 of our acyl chlorides unreacted. Okay, we'd need another equivalent of nitrogen to come through and actually react, okay, and pull or react with that species. As far as strictly balancing the equation, yes.
1 acid chloride and
2 amines. Yeah. Okay. Questions with your nitrogen nucleophiles? Okay. Hydrogen nucleophiles. Okay, we can supply hydride. How do we supply hydrides? Lithium aluminum hydride. What's that? And we do have the sodium hydride. Typically, sodium hydride acts as a base, not as a nucleophile. Okay, and it has to do with solubility issues. Don't remember in this case, but I think sodium borohydride can also be used. We'll see if that pops up or not. Okay. The issue with lithium aluminum hydride, if we start with the acid chloride, and we go through and we try and reduce this. There's our acid chloride, and we add hydride. Where's the hydride attack? Our carbonyl carbon. Now what happens? Break the pi bond, but then what happens? Reform the pi bond, and the Cl leaves. So the result takes us to the aldehyde. What's the issue with the aldehyde? Okay, we still have that carbonyl carbon. Lithium aluminum hydride was wicked reactive. What happens when it sees the aldehyde? Does it again. Okay? So if we're going to react hydride with an acid chloride, we don't see the aldehyde form because our aldehyde is still extremely reactive, and what ends up happening is that we then react all the way down to our primary alcohol. Okay? So we see that second hydride attack until ultimately we don't have a good leaving group anymore. Break the pi bond, but now there's no good leaving group, so we can't reform the pi bond. Our reaction kind of stalls out. Okay? So just something to be aware of when you're reacting with your hydrides. Seems a bit of a silly reaction if you ask me to go through and do this. Okay? Any guesses why? Acyl chloride was ridiculously reactive, our highest reactivity species. To get it to that point, we had to use dangerous chemicals. Why would we get it to the most reactive thing we could when pretty much any stage underneath it would have worked just as well with the hydride? Okay, it just doesn't make sense, okay, to use it as a nucleophile with your acyl chlorides. It is still reactive in that way, but you'd very rarely see that just because there's no reason to get you to that point where you would want to use the hydride. Okay? Yes?
Are there any more mild agents you would use to stop the aldehydes?
I don't remember. Here we go.
Oh, there we go.
So if we wanted to stop at the aldehyde, what we would need to do is somehow inhibit that second hydride from coming in and reacting. Okay? And I know that whenever we draw this out, and I just drew it out like that too, I draw it out as H minus comes in and does its little thing, right? How big is H minus? Very, very small. So how is making a bigger H minus even possible? It's not. So why is this a valid thing to talk about? Okay, well, when we look at the mechanism for your lithium aluminum hydride, okay, this comes back to why sodium hydride doesn't work. It's very insoluble, so we have to use something that can stabilize the hydride long enough to get it to the reactive site. To do that, we bring in our aluminum, and what happens is our hydrogen coordinates to the carbonyl carbon, and the aluminum coordinates to the oxygen. Okay? Both of those conditions must be met for the hydride to attack. Okay? So what happens? Oh, those dots don't show very well. We have to have both of those conditions met. Okay? In the case of the acyl chloride, that is a ridiculously good electrophile. So it is going to start to overcome a lot of, or any steric effects that really get thrown at it. But what happens when we move to the aldehyde? Okay, the aldehyde is still reactive, but it's nowhere near as bad because we don't have that leaving group. Okay? So what can end up happening in this case? Well, we still want the aluminum to coordinate with that oxygen, and we still want our hydrogen, or hydride, to coordinate with our carbonyl. And in the case of lithium aluminum hydride, that works. But what happens if instead of lithium aluminum hydride, that was a nice pentavalent carbon there. We did something with big old alkyl groups hanging off that aluminum. Those alkyl chains now prevent the aluminum from lining up with the oxygen. If it can't line up with the oxygen, the aluminum can't get the hydride, the carbonyl carbon. So what ends up happening? Nothing. The reaction stops. Okay? It can't propagate any further. So if we want to stop at the aldehyde, what we would end up using is a very bulky reducing agent. Okay, so we would take some, let's see, they give an example here? Yeah. Okay, in this case, they're using, I don't even know if that has a name. We still have our aluminum hydride, but now we have these OR groups out on the sides. Okay? In this case, those oxygens are doubly important. Not only do we have this bulk of those R groups, but what do those oxygens do? Particularly with their lone pairs. They can share electron density with the aluminum, which does what to the aluminum's reactivity? Decreases it. So now it's less likely to even want to coordinate with the oxygen from our aldehyde. Okay?
It reacts with acid chloride
because the acid chloride is that reactive. Yep. Okay. But the aldehyde, not quite polar enough for it to really get in there, or a little bit less reactive. And our aluminum structure is so sterically blocked that it kind of prevents that association. Okay. Again, I'm still not convinced that we would really be looking at this kind of chemistry. I mean, it's possible in this case to get to your aldehyde. The alcohol doesn't make much sense. Okay. Carbon nucleophiles. We don't have a whole lot of carbon nucleophiles. I know I said et cetera there. That was kind of a misnomer. Okay, we've got Grignard reagents. We've got acetylides. What other nucleophiles can you think of? Say that you were just tested on. Cyanide, that's another good option. Your alpha carbons, your enolates, are also reasonable nucleophiles. All of those are going to be very inclined to react with your acid chlorides because that carbon is now extremely electrophilic. Okay? Just as we saw with the other ones, oops. Okay, with your Grignard reagents, how many equivalents do we end up seeing? Okay. We'll see a 2 equivalent option show up. Why would we see a 2 equivalent option show up? What happens after the first reaction with your carbon nucleophile? There's our carbon nucleophile. It comes in and attacks. What breaks? Pi bond. What reforms? What happens? Chloride. And what do we end up with? Our carbon-carbon bond, which is pretty important. But then also, what do we still have? We still have an electrophile. So if I do 1 equivalent with an acid chloride, I can stop at a ketone. Okay. What if I do 2 equivalents? I can now push that down to my alcohol. And in this case, you're right, it would be a tertiary alcohol. Okay? Because we can react a second time. Is this something we need to be strictly concerned about? Okay? If I only add 1 equivalent of the acid chloride, where do you think we'd add or end? The alcohol or the ketone? Why end at the ketone? Well, when we did it with the hydride, we didn't end at the aldehyde. We ended at the alcohol. Which is more reactive to your carbon nucleophile? The acid chloride. So what would be your preferential reaction? To continue to react with the acid chloride, not with the ketone. Okay? Slightly different situation than from the ester. With the ester, that oxygen could resonance stabilize. Okay? Your chloride doesn't do as good a job of that. Okay? So we could take it to the ketone or potentially all the way down to the alcohol, depending on how many equivalents of the Grignard we added. Okay? Your Gilman reagent, effectively the same thing. I was pretty sure I was supposed to go back and re-talk about a large portion of that section from our last chapter and forgot about it. It's not like it's all that important anyway. Your Gilman reagent is your other nucleophilic carbon. To get those, we can use that organocupric stuff that we were talking about before. So you can react your acyl chloride with that organometallic, and you get the same kind of idea. You'll end up with your ketone. Okay. It's a little bit less reactive. It's not ever going to push to the carbonyl, or sorry, to the alcohol. Why?
Steric hindrance.
Interesting argument. Didn't think of that one. We do potentially have some steric hindrance issues. What's the other issue? The carbon-copper bond is a little bit less polar than the carbon-magnesium bond. And that's because copper has a higher electronegativity than magnesium, which means less polarity, which also means less nucleophilic. Okay, so it's not going to quite react the same. Okay? So acid chlorides. Okay, your textbook has a couple different summaries. I think they've got these individually for each of the different acid sections or acid derivatives. Ultimately, what we're trying to do is make the acid chloride with your thionyl chloride. Once you've got that, any nucleophile you can think of, it reacts. Okay? And they just happen to list off however many that is, something like 8 different nucleophiles. Okay? Each of those are effectively doing your same kind of general idea. Okay? You need to be kind of familiar with those. To me, it's not a memorization aspect. Okay? What you need to focus on is that your acyl chloride supplies what? An electrophilic carbon. To react with that, what do we need? A nucleophile. Okay? You do have to be familiar with all the different types of nucleophiles and where they can come from and how strong they are and all of that. But ultimately with your acid chlorides, because it is so electrophilic, any nucleophile you throw at it, it is going to react. Okay? And that's what they're trying to show with giving you all of these possible options. Okay? So start to think about your nucleophiles as hydrogen, getting hydrides in there. Carbon, you're looking pretty much at your Grignard reagents. Oxygen, you've got your alcohols and waters. Nitrogens, you've got your amines. So you really have 4 different types of nucleophiles. See what changes about the structure and adjust whatever piece you need to go ahead and put in there. Okay? The rest of the derivatives are ultimately kind of the same idea. So we've addressed that acyl chloride or your acid chloride up top. The next one is looking at your acetic anhydrides. Okay? To get that to go through and occur, we still go through that tetrahedral intermediate, except the nucleophile that we use in this case is the carboxylate. Okay? That goes through and attacks our electrophilic position, and we generate our anhydride product after some arrow pushing. Okay? Nice, straightforward, very similar to the exact, or effectively the exact same mechanism that we looked at in general format already with our Z and our N. Okay? We don't have to worry about any protonations or deprotonations in this version of the mechanism because we started with the carboxylate. If we started with the carboxylic acid, what would we have to do first? You react the carboxylic acid with a strong base first, then add your acyl chloride. You would still want to do pyridine with the carboxylic acid first. Get your nucleophile set and ready to go so you don't have to worry about any secondary chemistry. Okay? Your anhydrides tend to show up in a lot more frequently than your acyl chlorides. Okay? We've seen them in lab for that matter. I believe it was the Tylenol lab. We used acetic anhydride, which is effectively what we have here. Except in this case, or in that case, instead of these being R groups, you have methyls. CH3s, and we now have acetic anhydride. Okay. Why would we push to anhydrides instead of acyl chloride? It's less reactive, so it's a little bit safer. When it decomposes, we don't have to worry about the chloride and some wicked reactive thing. When your or your anhydrides decompose, particularly in the presence of water, turn them into two equivalents of carboxylic acids. Okay? So it splits open. We're relatively benign reagents. Whereas with the acid chlorides, we could end up generating a carboxylic acid and that chloride. We might get some small concentrations of HCl, a lot more dangerous to work with. Okay? So a lot of the reactions you will see come back to your acetic anhydride or your anhydride structures. Okay? So if we again look at our structure of our anhydride, where's our electrophilic carbon or atom? It's our carbonyl carbon. We typically go with either one. The main reason why we can pick either one is, what can you tell me about the R groups? They are almost always symmetrical. Very, very rarely will you see those be unsymmetrical. The reason being, when we run a reaction, we want one electrophile reacting with one nucleophile. Okay? So you can see all sorts of, oh, look, we can make unsymmetric anhydrides. That's fine and dandy, but it's effectively useless because we won't go through and react that species with anything. Okay? We just mentioned why we don't need the pyridine, because we have to generate our carboxylate salt first. Once we've got the carboxylate salt, there's no hydrogen to remove. We don't have to worry about it. Okay? So you won't see the pyridine show up in it. You will always see a carboxylic acid as a secondary product. Okay, why? What's our leaving group? Well, effectively a carboxylic acid. So when you react your acetic anhydrides, you will always see that carboxylic acid product generated because it's going to show up. It's your leaving group is effectively a carboxylic acid. Okay? This can also be a disadvantage in your reaction. Why? Carboxylic acids still have reactivity. If we look at the chloride as a leaving group, that's great. Pretty much dead in the water. We don't really have a lot of things that chloride can do. Carboxylic acid has a lot of extra functional groups. It can go through and do a bunch more chemistry. Okay? So as far as a byproduct issue, we typically don't like it because of that extra product, but safety-wise, it's a better option. Okay? Your anhydrides, again, very, very reactive, much like the acyl chlorides. So we can go through and react them with our alcohols or our amines and generate products out of this. Okay? Like we did in lab. In fact, this is effectively what we were looking at in lab when we looked at Tylenol. Okay? We started with what? Kind of. Still not quite what I wanted, but yes, very, very close. We started with this guy. Whoops, go away. And kind of the idea behind the lab was to find out where our acetic acid or acetic anhydride reacted. Where did it react? With the nitrogen or with the oxygen? Good quiz question, by the way. With the nitrogen. Why would it react with the nitrogen? Nitrogen is less electronegative, which makes it a better nucleophile. Yes? Acetic anhydride. With our nitrogen instead. Okay. So given the option, we would push to the nitrogen acting as our nucleophile instead. So both nitrogen and oxygen can act as nucleophiles. Like I said, we've got those as possibilities. In one case, we end up with the amide functional group. In the other case, we end up with the ester. I included these just because we made Tylenol. Okay? So we saw that reaction and saw that the acetic anhydride went to the nitrogen position. If you take a look at both aspirin and Tylenol, they are commonly synthetically made using acetic anhydride. because you can get very high yields of your product in that case. You could potentially even recuperate the acetic acid molecule that's kicked off and reform that into an anhydride. Interesting idea. Okay. So we will end there. Pseudo-mercifully. Okay, cool, there it is. Got through anhydrides. Okay. Esters are going to be a little bit longer for a discussion, and the amides will have some extra kind of special chemistry with them, but ultimately it's all the same chemistry. We've got the electrophile on the acid anhydride, or on our carbonyl, react it with a new nucleophile. React it with a new nucleophile. All the way through. Okay? And I will try and get sapling up and running and keep it short, I promise. Worst case, it'll be so short it won't exist. Is that all good?
Yeah.
I went over this with